So let's get going. I'm looking at class G, which is more logarithms and simple interest. So let's get started. So I want to first look at solving the following couple logarithmic equations. Just to remind ourselves of how logs work. Actually, before we do these first couple problems, I just want to remind you of two important facts about logarithms. If you have the log base b of b to the x, that is equal to x, because we're saying b to what power equals b to the x. Well, of course, b to the x power equals b to the x. And the other, I'm just have to look at my phone because the noise is going to get to be too much for me. Sorry. All right, I'm going to pay attention to my phone, maybe. The other important thing I want to mention is that b to the log base b of x is equal to x. I know I mentioned a couple examples of this last time, but I just wanted to point out that these things are true. This one especially comes up a lot. So if you're like doing, e to the natural log of 5, that's just 5. Or if you're doing the log base 4 of 4 to the 7th power, that's just 7. So there's just a couple of log rules that really come up quite often. So I want to make sure everyone is very, very aware of those. Okay, so let's get on with things. So I want to look at these couple questions here. First one, or things I want to solve for x. This one looks kind of complicated. It's log base 9 of log base 2 of x equal to 1/2. And the idea here is that we want to use our ability to rewrite these logarithmic equations as exponential equations. So I'm looking at this as log base 9 of a thing. See that better maybe? Yeah, log base 9 of a thing. And I know I can rewrite this as 9 to the 1/2 equal to this stuff in here. So I say my base is 9, my power is 1/2, and it's equal to that. Log base 2 of x. And now I want to simplify. I know that 9 to the 1/2 is just the square root of 9, which is 3. So 3 equals log base 2 of x. And then I'm going to solve for that in the same way I just did the first part. I'm going to rewrite this as an exponential equation. My base is 2, my power is 3, and it's equal to x. So x is 8, my favorite number. And we can plug it back in if we really wanted to, right? If you plug in 8, log base 2 of 8 is 3, and then log base 9 of 3 is 1/2, because 9 to the 1/2 power is 3. So look at this next one. 10 to the 2x minus 3 equals 4. So there are a couple ways you can do this problem. You can rewrite it using just a logarithm, right? You can say, I know how to rewrite an exponential as a log. So one way to go is to say, I'm going to write this as, I know my log base 10 of 4 is equal to 2x minus 3. That's one way to go. Let me talk about the more kind of typical way people usually do this stuff. Often when solving an equation where you have a variable in the exponent, we solve this just by taking the log of both sides, either the natural log or the log base 10. Usually I default to the natural log. In this particular example, I would default to log base 10 because there is something that has a base of 10 already. So I would rewrite this as log. We don't have to write the base 10, right? When you write just log, the assumed base is 10. Log of 10 to the 2x minus 3 equals log base 10 of 4. And then I'm going to use that thing I just talked about, that if you have log base 10 of 10 to the something, since those bases are the same, log base 10 of 10 to a thing is just the thing. So that's just 2x minus 3 equals log base 10 of 4. Right? Those equations are the same. So you can do it either way to get to this place. And then the rest of it's just solving for x. I'm going to add 3 to both sides, so that 2x equals 3 plus log of 4. And then finally divide both sides by 2 to get x equal to 3 plus log of 4 divided by 2. You could also write this as 3 over 2 plus log of 4 over 2. And then actually, if you really wanted to, you could rewrite log of 4 as log of 2 squared over 2. And then you can bring that power down in front and say x equals 3 halves plus 2 log of 2 over 2. And then those 2's cancel, and you get x equal to 3 halves plus log of 2. I don't think you need to do this right now. Like, I think this answer is a perfectly acceptable answer, but I mentioned this because, especially like if you're going, I feel like especially in the 17 series, but really any class, a lot of times you will see people do this sort of simplification, and it's good to know what's going on. Why someone might jump from 3 halves plus log of 4 over 2 straight to 3 halves plus log of 2. It's because they are doing all this work. Oh, sorry, I didn't have the chat up. Someone wrote something in the chat and I missed it. Sorry. Log cancel. So here's what I would say. It's not that they so much cancel, although it's fine to think of it that way, but what's really happening is they're undoing each other. So, right, when we see this here, I'm assuming you're talking about this part specifically. When I see this, right, so just like when I see log base 2 of 8, the thing I'm saying in my head is 2 to what power equals 8? And the answer is 3. Here I'm saying 10 to what power equals 10 to the 2x minus 3. Well, of course, the power has to be 2x minus 3 because 10 to the 2x minus 3 equals 10 to the 2x minus 3. But yes, a shorter way of thinking of it is just that they cancel out. But I like to think of it as undoing each other because it's a little bit more, it's slightly more correct language to think of the log base 10 and 10 to the something as undoing each other. But yes, it is something that happens all the time. So as long as the bases are the same, they undo each other. Really, you could also write log base 2 of 8 as log base 2 of 2 to the third. And then you're saying, oh, 2 to what power equals 2 to the third? Well, of course, it's 3. So the log base 2 and the 2 to the part cancel each other out or undo each other, as I would prefer to say. Yeah, excellent. All right, let's move down the page here. So I'm looking at page 2 of the notes here of class G, and they give us some information to start off with, which are the following approximations. We are given here that, I'm going to write them all down. So that log base 10 of 2 is approximately 0.30. And the log base 10 of 3 is about 0.48. And log base 10 of 7 is about 0.85. And then they give us the same approximations for the natural log. They give us the natural log of 2 is approximately, I should know these ones, I feel like, 0.69. And natural log, which is log base E. Natural log of 3 is approximately, I think, 1.19, 1.10. Natural log of 7 is approximately, right here, 1.95. Oh, and they also give you natural log of 5. Natural log of 5 is approximately, I got here, 1.61. You don't have, sorry, I should have said this in the beginning. You don't need to write these down, right? You can look them up or see them on the notes or use the calculator. But here's what we want to do with this. So we were going to use these to then say, what's the natural log of 21 approximately equal to? Oh, sorry, well, we'll do natural log and we'll do log. Why not? So the idea for both of these is that really this is a test of our ability to use the rules of logarithms to write this as something we already have. So I write natural log of 21 as the natural log of 3 times 7. And then I can use the product rule for logarithms. It says if you have the log of something times something else, it's equal to the log of the first thing plus the log of the second thing, whatever your base is. So natural log of 3 times 7 is the natural log of 3 plus the natural log of 7. And then we can use that there are approximations. We know that natural log of 3 is approximately 1.10. The natural log of 7 is approximately 1.95. And then we can add them together and get that it's approximately 3.05. It's not going to be exact, but it's going to be close. Same idea here, right? In fact, it's the very most same idea. You can write this as log base 10 of 3 times 7, and then that's going to be log of 3 plus log of 7. And then that's going to be approximately 0.48 plus 0.85. And adding those together, we're going to get, let's see, 1.33. So log of 21, or log base 10 of 21, is approximately 1.33. All right, let's do a few more. So these first ones I think are pretty straightforward. They want the natural log of 10. How can I break up 10? Well, there's only one sensible way in this context to think about multiplying to 10, which would be 2 times 5. So that's going to be the natural log of 2 plus the natural log of 5. Natural log of 2 is about 0.69. Natural log of 5 is about 1.61. And adding those together, we get 2.30. So I want to repeat here. The point of this isn't to know what the number is at the end. Like, the number at the end doesn't really matter. The point of this really is to understand how you can break up the logarithms into pieces so that then the pieces look like things that we already have listed out for us. I definitely saw questions like this. It's a little bit more challenging on the 17A homework I've been helping students with. So this is something that if you're taking the 16 or the 17 series, or any of the A classes, 16A, 17A, or 21A, you will definitely be having to do things like that. Definitely the most in the 17A class, though, for sure. All right, let's see if this pen's any good. A couple more. So this one's going to be a little bit harder. How about the natural? So the following: the natural log of 0.6. Yeah, I don't have a 6 anywhere. Right? I could write this as the natural log of 6 over 10, and then write it as the natural log of 6 minus the natural log of 10, but I don't have a 6. So what I should actually do, what could I do with that 6 over 10? Sorry, I want to change my video settings just a little bit here.
Divide by 2.
Right. I can totally divide the top and bottom by 2 and write this as the natural log of 3/5. And then we do have the natural log of 3 and the natural log of 5. So we can write this as the natural log of 3 minus the natural log of 5. And that's going to be approximately the natural log of 3, which is 1.10, minus the natural log of 5, which is 1.61. So we get approximately negative 0.51. Something worth knowing here, when you take the natural log of something that's less than 1 and bigger than 0, because it has to be bigger than 0, or the log with any base, if the stuff in here is less than 1, the answer is going to be negative. Similarly, right, if you take the log of 2/7, 2/7 is definitely less than 1. We know we're going to get a negative answer. Right, that's going to be the log of 2 minus the log of 7. And that's going to be approximately log of 2, which is 0.30, minus log of 7, which is, where'd you go? 0.85. And that's about negative 0.55. Right, last one on my, let's do, sure, let's do two more. Yeah, I like this one. How about the natural log of 0.75? It would probably be good to express this as a fraction. So I'm going to write 0.75 as 3/4. And then I can rewrite 3/4, or I can write the natural log of 3/4 as the natural log of 3 minus the natural log of 4. I know what the natural log of 3 is. I don't know what the natural log of 4 is, at least it's not on my list, right? So what I can do is I can write this as the natural log of 3 minus the natural log of 2 squared. And then I can use the power rule for logarithms to bring that 2 down in front. So that this is the natural log of 3 minus 2 times the natural log of 2. And then that's going to be approximately the natural log of 3, which is 1.10, minus 2 times the natural log of 2, which is 0.69, I believe, yeah. So that's going to be 1.10 minus 1.38, which is going to be about negative 0.28. All right, I want you guys to try this next one. So I'll give you like a minute and a half to try and simplify the natural log of the square root of 4/15, which I would immediately encourage you to rewrite as the natural log of 4/15 to the 1/2. All right, I'll give you 90 seconds to work on that one. All right, so here's how this one should work out. The first thing we really have to do here is bring this 1/2 in front. Right, this is 1/2 natural log of 4/15. You break this up as 1/2 times. Now it's going to be 1/2 times all of this. Natural log of 4 minus natural log of 15. Natural log of 4 we're going to deal with in the same way we did before. It's going to be natural log of 2 squared minus natural log of 15 is going to be the natural log of 3 plus the natural log of 5. Now watch out. I'm about to make a mistake here. So there is an error there. And the error is that it should be minus natural log of 15. So it should be minus all of this, meaning I should have some parentheses around that right there. So let's do a little more simplifying. This is going to be 1/2 times 2 natural log of 2 minus natural log of 3 minus natural log of 5. Because I'm distributing that minus sign to each of those things there. All right, so then I'm going to get approximately 1/2 times 2 times 0.69 minus 1.10 minus 1.61. And I threw that into a calculator because I didn't want to calculate. Also in the notes, it was actually a cube root instead of a square root, but it's okay. This is approximately, sorry, negative 0.665. So, any questions about this stuff? There's definitely some questions in the homework where you're going to be asked to do the same sort of thing. You're going to have log of a number. You're going to have to break it up into numbers that you can actually kind of tackle.
Wait, I have a question for, I thought you could multiply 4/15 by 1/2.
So I can't multiply 4/15 by 1/2. I can multiply the natural log of 4/15 by 1/2.
Wasn't there like a rule where like you can multiply it by the exponent?
Well, one thing you could, a different way you could go, you could write this as the natural log of 4 to the 1/2 power over 15 to the 1/2 power. But we can't. But we can't actually multiply those numbers by 1/2.
Thank you.
It's a good question. Other questions? Oh, that went down just a little bit the wrong way. Okay. I wonder if anyone's had to have like, I wonder if anyone's students have had to call 911 because their teacher started like choking in the middle of class. I don't intend for that to happen here, but I have to imagine there's been someone teaching a class and they've had an emergency and students have had to call the appropriate people. Usually I would just say my wife is here, I'd be fine, but my wife is not here right now. So you guys, if I looking bad, call someone, but I don't intend for that to happen. All right. Anyway, enough with the morbid thoughts. Let's move on to the next part of this section, which is talking about simple interest. So simple interest really is a precursor to talking about compound interest, but we have to talk about simple interest first. So simple interest is money you can earn by initially investing some amount of money, the principal, at some percentage of interest. And then at that percentage, the interest is added every year, making your investment grow. We'll talk about compound interest in the next class, but the idea here is with simple interest, you're only getting interest on the principal and not compounded on the other interest you have earned. So let's say we invest $1,000 in a bank account. Invest seems like the wrong word. Maybe deposit $1,000 in a bank account that earns 5% interest every year, which is certainly, this question was written in a different time when interest rates were much higher. How much money will there be after 1 year? So let's, and we'll look at years. So 1 year. Let's do it this way. So after 1 year, I'll still have the $1,000, right? So I want to really think about it as the amount is going to be the principal plus the interest that we earned. So in this particular case, the amount, we usually like to write the amount as a function of time. So we typically say the amount at time t is the principal plus the interest. And in this particular part, the amount after 1 year is going to be the $1,000 we start with, plus the 5% interest we earned. So how do we calculate 5% of $1,000? We multiply $1,000 by 0.05. Now be careful. I've definitely seen people accidentally, when they're changing a percent to a decimal, forget that zero there, right? If it's 5%, it's 0.05. If it's 50%, it's 0.5. So make sure if it's a single digit percent, like 8%, it's 0.08. Make sure you remember that zero that goes after the decimal before the number. So 0.05 times 1,000 is 50. So I get $1,000 plus $50, which is $1,050. So that's how much money I'd have after 1 year. And interesting. So you could talk about simple interest. I was wrong. We're actually talking about compound interest today as well. At least, well, yeah, okay. Yeah, sorry. So I made a small error when I said a thing. It's not that big a deal. But we do now say that we have $1,050 in our account. So how much money am I going to have after another year? Well, now I'm going to earn 5% interest on the amount I have. So we actually, this is still really compounding interest. It's just we're compounding it every year. When we talk about real compound interest, you start compounding it more than once per year. So how much am I going to have for 2 years? Well, I'm still going to have my $1,000. I still have my principal. Then I'm also going to have the 5% interest I just earned. So the 0.05 times 1,000. And then I'm also going to have in the next year 5% interest earned on this amount of money. So I'm going to have plus 0.05 times this amount here. And I want to show you some math that kind of ends up feeling like it looks a little tricky. It's really not that tricky. It just kind of looks a little tricky at the beginning. This is 1,050. And this is 1,050 times 0.05. I'm going to say this is 1,050 times 1. And from each of these, I can factor out a 1,050. So this is equal to 1,050 times 1 plus 0.05. But 1,050 is really 1,000, right? This is my 1,050 here. This is really 1,000 times 1.05. Right? If I factor out 1,000 left with a 1, factor out 1,000 left with 0.05. So this is really 1,000 times 1.05 times another 1.05, which is 1,000 times 1.05 squared. So interestingly here, after 1 year, we have $1,000 times 1.05. After 2 years, we have $1,000 times 1.05 squared. And if we actually, if you get a calculator out and calculate this, this is approximately $1,102.50. Right, we earned just a little bit more than $50 of interest that next year because we had a little bit more principal to earn interest on. And then we could do the same thing for year 3. The numbers start getting a little bit wacky. Right, we could say that, okay, in year 3, I'm going to have all the stuff I had from year 2 plus 5% of that. Right? Each year, you're just getting 5% of what you, an additional 5% of what you had of the year before. So look, I can totally factor out the the A of 2. I'm left with a 1 plus 0.05. So A of 2, the amount we had after 2 years, we just calculated on the previous side of the board, that was $1,000 times 1.05 squared. And now I'm multiplying by 1.05 again. So after 3 years, I get $1,000 times 1.05 cubed, which is approximately, the numbers aren't really super important here, but it is approximately $1,157.63. So again, we got a little bit more than $50 the next year, right? So this first year, we got $50 of interest. This next year, we got like $52.50 of interest. And this next year, we got like $55.11, right? So each year, you're getting a little bit more interest because you have more principal to get interest on. So here's the general formula for simple annual interest. The amount of money you have after T years, so this is the amount after T years, is equal to your principal, that's just your initial starting amount, times 1 plus your interest rate as a decimal. So rate as a decimal to the Tth power, where again, T is the number of years. So that is how you calculate how much money you'll have after T years if you've invested some principal at some interest rate that's compounded yearly. All right. Then we're going to do a few problems. You should. Sorry, you scared me a little bit. One second. Before you jump in, I just want to say you should definitely be using a calculator to calculate the things we're about to calculate. Go ahead.
Just quickly, AT. So what does it say on the bottom? Sorry, I can't really read that.
So one thing I would encourage you to read this as A of T, right? A is a function of T, and it says the amount after T years, and really I should say the amount of money after T years.
Okay, thank you.
Oh. All right, so we're just.
Okay.
No, you go ahead.
Is it P plus 1 plus R or just P times?
P times.
Okay.
To the T, right? So it's P times 1 plus R to the Tth power. Any other questions? Wow, time's really flying by here. I better speed things up. Oh yeah, we'll do it. Okay, so for these calculations that we're about to make, I will again say you really should use a calculator. It is certainly possible to do it by hand, but it would be very time consuming. I know, and I also know that the last page of these notes say like, feel free to use a calculator to help you on your homework. Remember, you're not allowed to use calculators on midterms. That comment might not really be so applicable this particular quarter, but we'll tweak it. So I will definitely make it clear. I mean, I can't imagine telling you guys you couldn't use a calculator on your midterm, right? Because I'm not going to enforce that. So yeah, that seems ridiculous. So here's the first example. Maria opens a savings account that pays 5% annual interest. 5% interest. And she puts in $100. So $100 is the principal. 5% interest, so that means that the interest rate is 0.05. The question is, how much money is in the account after 5 years? So T equals 5 years. So this is really just to throw the stuff into the formula and see what you get. So my amount after 5 years is going to be my principal, which is $100, times 1 plus my interest rate, which is 0.05 to the 5th. Simplifying just a tiny bit, that's $100 times 1.05 to the 5th power. 1.05 to the 5th power is not something I'm good at calculating, right? I'm going to put it into the calculator. 1.05 to the 5th. That's 1.27628. So this is going to be approximately $100 times 1.27628. Multiplying by 100 is going to move the decimal over 2 places. This is going to be approximately $127.63. And that's what I got my answer as. In this class, I wouldn't stress too much about trying to decide where you should cut off the decimal. I would say if you're talking about money, you should round to the nearest cent, right? It doesn't really make sense to talk about fractions of cents, at least not in this class. The second question, and so I will say just generally, for these types of situations, there's really only 2 sorts of questions we can ask. I can ask you, after so much time, how much money is there? Or how long, how much time does it take until there is a certain amount of money? This first one is, I gave you the time, I asked you how much money. This next one is, I'm going to give you how much money I want there to be, and I'm going to ask you to find the time. So how long until there's $1,000? Another way I could have phrased that question is how long until the money multiplies by a factor of 10? But it seems like a weird phrasing. So we're just going to take this equation that we have, this amount of money at time t equal to $100 times 1.05 to the, right? We don't know what time is here. We're trying to solve for time, equal to 1,000. And we're going to try and solve this equation for time. So I'm going to divide both sides by 100. 1,000 divided by 100 is 10. So I have 1.05 to the t equal to 10. And now I would take a logarithm of both sides. You can either use natural log or log base 10. Normally I would use natural log, but here, since there is a 10 on this side, I'm going to use log base 10. So I'm going to say log base 10 of 1.05 to the t equals log base 10 of 10. Okay, everybody, what's log base 10 of 10? You can type it in the chat. You can show me on your fingers. I know there's no one has your picture of it. You can say a word.
1.
It is 1, yes, right? Because 10 to the first equals 10. Thank you for being brave. I appreciate it. You know, it's not always fun to talk into the ether here. So then I've got, so here's what I'm going to do. That's 1. And I'm going to bring this t down in front. So that t times log base 10 of 1.05 is equal to 1. I'm going to divide both sides by log of 1.05 to get that t is equal to 1 divided by log base 10 of 1.05. And that's my exact answer. And then I would throw that into a calculator and get the t is approximately 47.2 years. Okay. So, okay. Let's look at these last couple questions. I guess these questions were written super long ago if they're using Justin Bieber as a reference. Seems like a dated reference, but we'll go with it. Oh, wow, man, just, yeah. Love this pen dust all over my hands. All right, so suppose Justin Bieber puts $5 million into a savings account. So our principal is $5 million. Paying annual interest. Oh, and we don't know the interest rate. The interest rate is we don't know. After 2 years, we have a total of the amount of money after 2 years. So A of 2 is $5.5 million. The question we're trying to answer here is how to stop dropping the eraser. It's also how much interest was he earning per year. So we're trying to solve this equation. So here's our usual equation. Amount of money at time t equals the principal times 1 plus r to the t. And here's what we know. We know that T is 2. The amount of money after 2 years is $5.5 million. I'm not going to write the dollar sign because I don't really need it. The principal is 5 million times 1 plus r squared. So I'm trying to solve that equation. So I'm going to divide both sides by 5 million. I'm going to drop the zeros, right? I could write 5.5 million over 5 million, or I can write 5.5 over 5. I can cancel out all those zeros. You can write 55 over 50 if you wanted to, right? If you don't like that. And this is essentially going to be 1.1 equal to 1 plus r squared. And then that's 1.1. I'm going to square root both sides to get 1 plus r. So r is going to equal the square root of 1.1 minus 1. And that's going to be, using a calculator, interestingly, it's approximately 1.05 minus 1, which is 0.05. Yeah. So again, almost all these equations, you're essentially going to have all the pieces you need except for what, and then there'll be one thing left to solve for. So our job is just to make sure we fill in the blanks correctly and then solve using algebra appropriately. So I want to make sure everyone's cool with this. Right? When I really, just in case you weren't cool with that step, I just divided both sides by 5 million. So I had 5,500,000 divided by 5 million. And then I cancel all those. So I got 55 over 50, which is just 11 over 10, which is 1.1. There's a lot of different ways you could go there, but I just want to make sure everyone's okay with that. All right, let's talk about the last example here. Starts off by saying how, so you can think about simple interest, simple yearly interest being on money that's invested, but it's also true that simple interest applies to something like loans, because a loan is just money that someone has borrowed that someone else has invested. So a loan and an investment are really the same sort of thing. So when you borrow an initial amount of money, which is the principal, there is a percentage of the principal, which is interest, that is added back, making the amount of money that you owe grow. Sure, most of us are very familiar with the idea of loans when it comes to college, myself included. It's fine if you aren't. I hope none of you have any loans. I don't imagine that's the case. So suppose you borrow $20,000 in student loans this year, which I feel like is hopefully a high amount at UC Davis. So our principal is $20,000. And we're going to wait 10 years without making a payment. So no payments for 10 years. Give it as, well, yeah, not a great idea, right? We want to start paying our loans back sooner than later so that the principal doesn't grow so that the amount doesn't grow like it's about to in this example. How much money will we have accrued? How much money will we owe at the end of these 10 years if we were charged with a 6% interest rate? So first of all, we're going to write 6% as 0.06. And we're really just going to throw everything into this formula. In these problems, there's not a whole lot more than just throw your numbers in and see what happens. So here, the amount of money after 10 years, or the amount of money we owe after 10 years is $20,000 times 1 plus 0.06 to the 10th power. So that's 20,000 times 1.06 to the 10th. I'd put 1.06 to the 10th on my calculator and get, what do I get? 1.06 to the 10th power is 1.79084. So I get approximately 20,000 times 1.79084. 47697. Not quite double, right? If it was if we had 2.0, that would be double the amount. But if we multiply that by 20,000, we end up with $35,816 and 95 cents. So letting money accrue interest for 10 years at an interest rate of 6% doesn't quite double the principal, but it comes close.